Hello, everyone. Welcome back to Physical Geology 1403. Today is lecture 10. We are going to learn about deserts, not desserts. Check that spelling, right? No two S's, just the one. Okay. Desserts have layers. Jocelyn can make us a multi-layered Earth-shaped cake, right? That's funny. Okay, a few announcements. We are having our class movie night on October 4th. It will be in that room next door, Wood Math and Science 203. It will be at 6 p.m. That is a Friday. We are watching 2012. I did go back and look at the poll a few days ago. I already have announced that 2012 was the winner, but I went back and some more people had voted such that San Andreas and 2012 were tied. Now, we can't do a double feature. That would be way too late. Like, we started at 6. We'd probably finish the first movie about 8:30 and then talk about it for a little bit, and then we do another one. None of us would leave until like midnight. I ain't doing that. That's too much for me, let alone y'all. Okay, so if you all here want to, we can have a tiebreaker vote between those two movies, or we could just keep it on 2012. So how many of you want to watch 2012? 1, 2, 3, 4. How many of you want to watch San Andreas? All right, easy. We're watching 2012 then. Easy tiebreaker vote. Okay, so yeah, October 4th, here, watching 2012. We're going to have fun. Again, you can bring snacks, food, drinks, whatever the heck you want. Bring friends, bring family. I'll have my son here with me, maybe my daughter. It depends on the day that she has. If she's too irritable, I might leave her at home. But my son usually comes with me. My 6-year-old usually comes with me to these movie nights. Let's see, what else? Huh? He's seen all these movies at least once before. Yeah, his favorite is actually the volcano movie, Dante's Peak. Yeah, he loves the volcano movie. He loves just talking and thinking about volcanoes. You're gonna make him into a geologist? He might. I have not been trying to sway him anyway. If he has questions about dinosaurs, I answer them. If he has questions about volcanoes, I answer them. He just naturally deviates more towards volcanoes than anything. And if he turns into a volcanologist, I would not be displeased. So we'll see. You have your second exam opening. Let's see. 1 week from today. Okay, that's when exam 2 is. So we get lecture 10 today, 11 on the next time we meet, and then exam 2 review, and the exam 2 will open 1 week from today. So in 2 videos from now, if you're taking this online. Okay. Hopefully by now, everybody has turned in every lab. I will be going through all of the lab submissions in the next few days and grading them. Anyone that has not turned in anything, as far as labs are concerned, and discussion boards, if you are doing discussion boards, any that have not been turned in for Module 1, I am going to start throwing zeros on. But like I mentioned in that class announcement the other week, that does not mean that it's a loss, okay? You can go back at any time, redo that assignment, and just let me know that you did. And then I'll go in and grade it. And you have the potential to get full credit for it. If you did the work to get full credit for it, you will get full credit for it. The 0 is there mostly to show you, hey, this is the consequence if you don't do the work. Okay, this is what your grade looks like with that 0 on there. Okay, are those overnight oats? Are those overnight oats? Nice. I used to eat those every morning. Those are good. Okay. Yes, please catch up. I will be giving you lab 5, which is not identification based, it is just reading maps. I will be giving that to you probably, I can give that to you this Wednesday probably. Okay, so you can try and knock it out of the way before we start hitting our round of exams. Because next week you have exam 2, and then you have the lab exam, and then you have the final exam. It's boom, 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 week after week. Okay, so I'm going to try and get you lab 5 on Wednesday, the next time we meet here this week, so that you have the opportunity to get that out of the way before we hit up all those exams. Sound fair? Sound good? Cool. Cool, 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 cool. So, what questions do you have for me?
What will the second exam cover?
Module 2. The second exam will cover Module 2. So, lectures 8, 9, 10, and 11. And because it covers half of the content, half the amount of content from Module 1, the exam is half the size. Module 1 exam was 40 questions. The Module 2 exam will be 20. Okay?
Yeah, that doesn't sound bad at all.
No? And you still get the full 500 minutes for it.
We need that in extra time, you know.
Yes. Extra time is good. Don't let it make you complacent. But yes, extra time is good. All right, what else? Hit me. What questions you got? Nothing? We talked about glaciers last time. No questions about glaciers? Have you heard or seen anything about glaciers between then and now that made you wonder, oh, I should ask Mr. Hart about that next time I see him? Nothing? I completely forgot to upload the pictures of me on that glacier in Alaska this summer. I'm going to try and remember to do that today. Let me write that down, actually. I saw some beautiful pictures of glaciers in Nunavut, Canada. You should look those up sometime. Just look up glaciers in Nunavut. They're beautiful. They're gorgeous. Let's see.
Is it true that the melting glaciers make the ocean up, like rising?
Yes, melting glaciers add to the height of the ocean. This is true. The elevation of the ocean rises as glacial melting increases. And where does that water go? Into the ocean. This has a few effects. Glacial melting has a few effects on the ocean. It does decrease the salinity of the ocean, mostly around wherever the glaciers are melting, but that fresh water coming out of the glacier makes its way through the ocean system and decreases the overall salinity over time. So that will affect the ocean chemistry. Diluted salinity can affect ecosystems. Okay, so there are certain organisms, many organisms actually, that rely upon a certain interval of both salinity and temperature. And as glaciers melt, they're adding cold, fresh water to the ocean, decreasing that salinity and decreasing the temperature, which is going to affect the ecosystems. Normally, we see some amount of extinction. It varies between being very aggressive extinction or very slight extinction in both ocean and on land as we are transitioning out of glacial cycles and into glacial cycles. It just depends on how quickly organisms can adapt, which is a concept we will discuss in more detail in Geology 1404. Okay, good question, good observation. Yes, it does change that. As for how it affects you and me, we will notice particularly in our day-to-day life whether the ocean is a little colder or a little fresher. What we will notice is that those sea levels are rising and impeding upon coastal communities. So places like New York City, for example, places like Hawaii, places like New Orleans, and similar situations all around the world. Those are just a few examples here in the US that relate to us. But any city anywhere near the ocean is going to feel the effect as sea level rises. Some cities, it won't take long. A foot or two of sea level rise, it's a lot more than you think it is. And there could be water in the streets, right? But then you think 70 years in the future, we're expecting 3 to maybe even 4 feet of sea level rise by the year 2100. That's a lot of cities and communities with ocean water in the streets at that point. Okay.
What cities will go under first?
What cities will go under first? Well, New Orleans is going to be a top contender for that title because they're already pretty far under sea level. New York, like I mentioned before, they're anywhere from 7 to 10 feet above sea level on Long Island and in the communities around Long Island. The National Oceanographic and Aerospace Administration, NOAA, which is the government organization that collects all the weather data. If you go to weather.com, they get their data from NOAA, okay? They have a model that you can run where you can basically drag a scale across the screen, and based upon current data, it will tell you what the ocean levels will be year after year as you drag that bar. So if you drag it to the 10 foot, which probably around 20, somewhere between 2100 and 2150, that's where we'll be at current projections, about 10 feet of sea level rise. A significant amount of New York City is underwater. Streets will become canals. Huh? That's cool? Not a fan of New York, are we? Huh? Walls? A seawall is something that is extremely difficult to build and maintain. A seawall is not ideal for, as we were going to talk about this when we learn about shorelines in a couple of lectures here. But a seawall is not ideal because think about how many billions of tons of water it is holding back. Okay? It's not a flood. It's not meant to contain a flood. It's meant to hold back the ocean. All that water pressing on this wall. It's an incredible effort to make something like that. And if there's a problem with it, how do you maintain it? You can't shut off the ocean to relieve pressure on the wall to fix your wall, right? It's a monumental effort to even consider how you would build a seawall that big, right? Possible, sure, but an incredibly monumental effort to pull it off. They'll do it for New York. Maybe they will. Who am I to say they won't? Who knows where thoughts will be 70, 80, 90 years from now? I probably won't need to worry about it. Some of y'all might. I probably won't. Regardless, the whole point of my PhD research is to try and encourage those coastal populations to be thinking about these questions so that they can start trying to find answers for that now. The easiest, I will say, in the long term, hardest in the short term, the easiest in the long-term solution, leave. Move. It's really hard right now to tell someone, hey, pick up and move your family inland because your great-great-great-grandkids will thank you. It's a lot easier to say, oh, the politicians will do something about it. No one's actually doing anything about it. They're throwing money at it. They're researching it. They're investigating it.
Throwing money.
Yeah, no, that's what they're doing. They're literally throwing money at this wall of climate change. We can't change it. We can stop our efforts to contribute to it. I won't say we won't. We can theoretically reach net zero emissions. And if we did that magically today, congratulations us, we are now friendlier as a civilization to our Earth. Whatever the consequences of that may be, maybe it sets our civilization back a couple of decades technologically, whatever that is, congratulations, we have reached net zero. global warming still continues. It would not stop. Okay? Ice would continue to melt. Oceans would continue to rise, at least for a couple more decades if we reached net zero. Okay? It's a train, right? It's not a car, it's a train. You can slam the brakes on your car and stop within a couple of dozen feet, right? Assuming that you're going a reasonable speed. A train takes about half a mile to stop, which is why if they see a car on the tracks, it's already too late for the people on that car, right? From the moment the engineer slams on the brakes, it takes the train about half a mile to stop. That's global warming. We are a train, okay? So instead of focusing so much on how do we stop this, which is a viable question, which should be explored and acted upon, okay? I want to focus my efforts more on what do we do anyway, right? It's not going to save many populations. If we reach net zero, many populations would not be spared the effects of global warming. How do we help those people regardless of where the people trying to fix the problem are at? I'm trying to play devil's advocate, I guess you could say. Okay? So things like relocation, planning infrastructure like desalinization plants. Do you know what desalinating is? When you take ocean water and evaporate it so that you're left with fresh water and salt. You can take the salt and you can put it wherever you want. Store it, use it for roads, sell it to go on people's tables, whatever the heck you want to do with it. But the important thing is you got fresh water out of the deal. That fresh water can get shipped to places that are experiencing water issues. That's the sort of infrastructure we need to be exploring. That's what we need to be building now in preparation for these issues that we will have in the future. Anyways, I will step off of my soapbox now. Any other questions? Okay, I love those questions. Keep them coming as you feel them, okay? All right, should we talk about some deserts? Yeah, who doesn't love talking about the desert?
Yay.
Yay! You don't love talking about the desert. Huh? We live in one? Do we? Ooh, let's talk about that. All right, when I say desert, what do I mean? Someone tell me what a desert is. A place that is deserted. Well, is a desert a place that is deserted, or is the word deserted come from a desert? Come from the word desert. Chicken and the egg situation there. Cade, what do you got? It's vacant. Okay, so we're looking at the word desert as if from the perspective of human population is what it sounds like y'all are thinking. This place is deserted. There is no one here. I'm talking about it in terms of geography. Dry, arid. What does arid mean? We'll talk about that. Huh? A place that receives no water, bless you. Yeah.
Isn't the Antarctic or something considered one?
Ooh, is Antarctica a desert? We will talk about that. Here I want to show you a couple pictures. Which one of these is a desert?
The one on the left.
This one? Is this a trick question? I can't answer that. If it's a trick question, I might give you a trick answer, wouldn't I?
Is the one on the left in Nevada
The
desert?
one on the right.
The one on the right is a desert, so that one's not?
No, my right.
On your right, my left, that's a desert. Okay, so this one's not.
That one.
They both are?
Dude.
Are they not very different from each other, though? How can both of these be deserts?
No one lives for miles.
But there's a road there. Obviously, someone lives here. Huh?
Arizona.
Huh?
Arizona.
What about Arizona?
I don't know. I was looking at the picture. That's what it looked like.
Yeah, a lot of Arizona looks like this. A lot of where we live looks like this, right? Okay. Yeah, what do you see that's different between these two?
Right one has it's like more loose sand, while the other one looks like it's more put together.
Okay, more loose sand, and this one has what? Hmm?
It's more compact.
Laura.
What do you see in this picture?
Like
There's plants, vegetation. May not be thriving, may not be lush and green, but how much more vegetation do you see in that than you see in this? A lot more. Okay, so let me ask you again, which one of these is the desert, or are they both?
this one is not a bit.
Which one of these is a desert, or are they both, or are neither? They are both deserts? What do y'all think?
In the orange one.
Huh?
It's only at this, the orange.
The orange one is the only desert here?
Say neither.
Oh, okay. When I say desert, this is typically the sort of image people imagine. This is the Sahara Desert in North Africa. Okay? Iconic, characteristic desert, easy to imagine desert. This is where we live, out here in this part of the world. You and I typically think, oh yeah, we live in a desert. But is it really the same desert? No. And yet, let's learn what a desert actually is. When I say the word dry, what does that mean to you?
With no water.
Receives no water, okay.
No water. Like
No water, little to no water. Okay, we're working with a range now. What else?
I imagine like cracks in the soil. Like where
Okay, there's some form of plant life, perhaps. What does plant life need? Water. Okay, so for there to be plant life, there would need to be that range, right? It can't be no water. It would have to be some water. So again, when you look at these pictures, how much water would you say this place typically receives versus that place? Both very little, but which one obviously receives more? Right, this one. Okay. Now, the word dry is tricky. Dry is totally relative. Drier than what? Right? The Odessa, Texas is drier than the Amazon rainforest. But the Sahara is drier than Odessa, Texas, right? Dry is relative. We can't really work with that. It's a descriptive, but not with any particular context, okay? Only comparison, but the comparison without really any data. So, arid, that's a term that we typically will use in science, okay? Aridity is measurable. Aridity is precipitation versus evaporation, okay? What is the amount of precipitation I receive versus evaporation? And for a place to be arid, it needs to have loss from evaporation be greater than the yearly precipitation. Would you say that here in this part of the world, we receive less precipitation than evaporates every year?
that's why we had the flood before, right? Like a little flash flood.
I mean, we got a lot of rain. That's why we flash flooded. But typically throughout the year, would you say that we have more precipitation than evaporation? Or the other way around? The other way around. And so, yes, we do live in an area that is arid. However, let's think about the Sahara. No plants, hardly any anyways, right? Very little life of any kind. Vast open swaths of sand. Oceans of sand, we call it at times. Would you think that their ratio of precipitation to evaporation is a little more extreme than ours? Yes. It is a very arid place. You could refer to where we are as semi-arid, if you will, and a place as extreme as the Sahara as truly arid. Okay? Now, There are a few things that play a role in this. Temperature, obviously, is one of those things, right? The hotter it is, the more water evaporates, right? True? True. But it's not only temperature. Radiation can also cause this evaporation. I don't know how many of you have had this experience, but you're driving down the road. It's the middle of winter, fresh snow on the ground. It is below freezing outside, and yet you see it's a beautiful sunny day. There is steam rising off of the snow around you. You ever seen this?
I don't think so.
If you grew up here, this is a very difficult thing to have seen because we don't typically get that much snow. But if you've ever been anywhere particularly far north or south, this is fairly common. Bright, beautiful, sunny day, below freezing temperatures, and yet steam rising off of the snow. And why? Because the solar radiation is evaporating the outermost layer of that ice, turning it into steam. Okay? So precipitation, or excuse me, temperature, mostly is that big control, but is not exclusively that control. Okay? Now, where do we get these deserts to form? There are a couple of zones around our planet that deserts tend to form in most commonly. Camera, stay with me here. There we go. All right, so the first one is low latitude. That is between the tropics of Cancer and Capricorn. This is the Tropic of Cancer right there at about 23.5 degrees north of the equator. And this is the Tropic of Capricorn, the same. Like a Capricorn, right? The tropics of Capricorn. No, Cancer and Capricorn, okay? So between those, we typically do not have, right at the equator, you typically will not have a desert. We'll talk about why in just a minute. But right there to the south of Cancer and around Capricorn, to the north and south of both of those, you typically will have deserts forming. Look at this, the Sahara, the Arabian. Over here with us, the Sonoran and Chihuahuan. Down in the south, the Patagonian, the Namibian, Kalahari, and this Great Sandy and Simpson. All of them forming around those tropics. And why? We'll talk about that in a minute. Then we have mid-latitude deserts. These are the ones that tend to form in the middle of continents, large land masses. The Sahara, yes, it's right there on that tropic, but also it's in the middle of a large continent, so that's a part of it. Good examples of this, the Gobi and the Turkestan, and the Great Basin Desert out here in North America, okay? Forming in the middle of these large continents, mid-latitude deserts. And then there are polar deserts. Now, Cade mentioned something very important earlier. He asked if Antarctica was a desert. What do y'all think?
Yes.
Why?
This is little water.
Ah, but isn't it covered in water?
Yes.
It doesn't evaporate. It doesn't evaporate.
What do you think?
I was to say void of life.
It's void of life, but again, that's not our definition of a desert, right? It needs to be arid.
Isn't there more evaporation? Because the ice doesn't melt because it doesn't absorb the sun's rays.
That's the kicker. Yes, Antarctica and a substantial chunk of the Arctic are covered in water, but it is solid water, not liquid water. So you can't really call it viable precipitation. It isn't liquid water. And therefore, yes, technically speaking, Antarctica and the far Arctic are arid because there is little to no liquid precipitation, and evaporation is greater than whatever amount they receive is. Okay? So yes, we call those polar deserts. Fair enough? Okay. Let's talk about these different locations where these deserts can form. Let's talk about low latitude first. Why do we get low latitude deserts forming around the Tropic of Cancer and around the Tropic of Capricorn? Where is the warmest place? Or I should say, where is the warmest zone around our Earth? The equator. Why is the equator so warm?
You receive the winds.
Mm-mm.
I feel like it's like the water thing.
No.
Hurricanes.
No.
The core.
No. I'm loving all these guesses, though. Keep them coming. Yeah.
And this is the sun.
Ah, it has to do with the sun. What does it have to do with the sun? Our orbit. Okay.
Isn't it where it
Gets it the
irradiates
most.
more?
Yeah. The equator. Notice when I hold this up, where is the equator? Is it going around the middle of our planet like this? No. It's going like this. The same angle as our tilt, our axial tilt. Okay. So why? Because Earth is spinning like so on its orbit around the sun, the area of the planet that has the most direct on exposure with the sun at any given point is along this line in the middle called the equator. Because it has the most exposure, the sun's rays have the least atmosphere to go through, basically. More heat is preserved along the equator, this equatorial zone. Therefore, it has more heat. What comes with heat? What happens to the water? Evaporation.
It rains a lot.
It rains a lot at the equator. I lived in Hawaii for 3 years. I lived in Japan for 4 years. I know exactly how much it rains in these equatorial zones. Okay. So there's a lot of it. There was barely a day that went by in Hawaii that it wasn't raining at least a little bit. It's extraordinarily humid. Now, warm air tends to hold water easier, more water, I should say, than cold air does. Okay, why? What happens to the water in the air when that air gets cold? It condenses. How many of you have ever had a cup of cold water sitting on, like you get a cup of cold water, you pour ice cubes in it, and then you set it outside on a table and you come back in 15 minutes. The outside of your glass is covered in water. Do you know why that happens?
Just water condenses on the outside.
Is the water from inside your glass somehow seeping outside of the cup to collect on the outside of your cup? No. Therefore, where is that water coming from? Yeah, the whatever water content is in the air around your cup. Exactly. The cool temperature of that glass, cooling down the water in the air around the glass, is causing that water to condense on the outside of your glass, of your cup. So cold temperatures causes water to condense out of the air. What happens when water condenses out of the air? We get what? Rain. So when you have very warm, very humid air from all of the evaporation at the equator, this warm air is rising higher and higher in the atmosphere. What happens to the temperature as you get higher in the atmosphere? Decreases. It cools off. Therefore, that humidity turns into rain. You get a lot of rain at the equator. However, there is something that's happening here at the same time. Convection. Y'all remember what convection is? It has to do with wind this time, but when we learned about it before, it was with a totally different context. Convection. It has to do with tectonic plates. That's a convergent plate boundary. Convection is the process that drives tectonics. How does it work?
Circulation.
Circulation of what? Heat is the mechanism circulating what? In the case of plate tectonics?
Energy.
Mantle rock, right? Hot mantle rock rises closer to the surface because it is less dense and therefore more buoyant. When it gets close to the surface, it starts to cool off and become denser, but it's also getting shoved off to the side by newer, hotter material beneath it. And so it gets shoved off this way and it gets cooler and denser and then sinks again to repeat the process. And you get this convection cell, this cycle of continually moving rock, heating and cooling, heating and cooling. That's what pushes on the bottom of our plates and causes tectonic activity. Well, the same thing is at play here, but with air. Bless you. At the equator, hot air rises, and as it rises, it starts to cool off. As it cools off, it rains out a lot of that moisture, but it's also getting shoved either north or south by the newer, hotter air rising beneath it. This cooling air is raining out all its moisture the further north or south it goes. And so finally, by the time it makes landfall again at the Tropic of Cancer or Capricorn, it has become cool, dry air. And because it is cool, dry air with hardly any moisture content, we get deserts that form around those bands of our planet, up here and down here, where they make that landfall, this cool, dry air. You following this process? Convection of air. It rains out that water as it moves north or south until finally cool, dry air contacts the ground again in those areas. That's how you form low latitude deserts. Now, mid-latitude deserts come in a couple flavors. Bless you again. Are you actually allergic to the snake? Oh, okay. If anyone ever was allergic to the snake, he would immediately go back in my office. Okay. There are a couple of ways that we can form these mid-latitude deserts, okay? They mostly happen inside of continents. Why would there be a desert inside of a large continent? What do you think? Take the Gobi, for example. Why would there be a desert inside of this large landmass? Yes?
It's not near the ocean.
It's not near the ocean. What would that have to do with anything?
There's less humidity,
Why would there be less humidity?
less evaporation due to the ocean not being there.
The largest source of evaporation on our planet is the ocean, right? So if I have a landmass large enough that some portion of that landmass is far from the ocean, that portion of landmass will receive less rainfall from evaporation, right? And so, yeah, we end up with this big old area in the middle of Eurasia that gets very little rainfall. The Gobi Desert just being one part of it. Okay, this entire area is pretty arid. Okay, some other places, the Sahara, out here. Okay, Australia, right there. Okay, large continents, large land masses tend to have large deserts in the middle. The best example of this being supercontinents that we have had in the past. We'll talk more about all the different supercontinents. What's the supercontinent that everyone knows about? Pangaea. Why does everyone know about Pangaea? It was not the first one. It was actually the last one. Yeah. All of these continents that we have today broke apart, are in their current arrangement after Pangaea broke apart. Okay, Pangaea broke up into what we have now. Pangaea is actually the last of many supercontinents that we have had on our planet. Not the largest either, only the most recent. But everyone loves thinking about Pangaea because dinosaurs, which is really funny because Pangaea had already started breaking apart before dinosaurs even showed up on the scene. Most of the time that dinosaurs were alive, our continents were in basically the same shapes that they are now. We'll talk more about that in 1404. That's not what happened in Ice Age. That's true. Sorry to burst your bubble. Now, Pangaea was a very large continent. And in the middle of Pangaea, huge desert, massive desert. Okay, how do we know that? We look at the rocks from that time. And a lot of it is indicative of desert rock, right? Middle of this giant continent, big desert. Okay. Then there is another type of desert that can form called a rain shadow desert. These typically form where prevailing winds carrying humidity with them run into an obstruction. And because of that obstruction, cannot carry that humidity over the obstruction. Ah, like mountains. Who can tell me where in the world this picture is from?
Chile.
Chile. Yes, this is Chile. Okay, the west coast of South America. This is the nation of Chile. Over here, Argentina, right? Huh? You don't think it's very chilly? I mean, right there, it's probably pretty chilly. What is this? Look over here. Here we have the Amazon. Nice, lush, green, all the way down here. But then we've got this desert. This is the Atacama Desert, by the way. How are we possibly going from lush rainforest to desert? And how could there possibly be a desert there when there's an ocean right there?
There's a belt with mountains.
What mountains might those be? What are these? What mountain range is this right here?
I've learned about it multiple times. I just don't remember the name.
No. What is the great big mountain range in South America? Any ideas over here? The big mountain range in South America? There is a delicious chocolate mint candy with the same name.
Almond Joy.
This is the Almond Joy range right there. No. That's chocolate coconut, but I do enjoy Almond Joys. But I like Mounds better.
Is it the triangle one? A triangle chocolate?
No, they are rectangular chocolates. This is not the Toblerone range. Any ideas, Sarah? No? This is the Andes.
I was about to say. Damn, I
Well, then why didn't you say Andes?
I didn't want to sound stupid.
No, man, you could not sound stupid.
The Andes?
No guesses in my class are stupid. Okay. The almond joys. Imagine saying almond joys. You'll know what candy I'm talking about, right? Have you ever had those? The Andes? I love Andes. Mint, top tier. Okay. Now, what happens here is because there is a mountain range here, the prevailing wind direction goes east to west. That's not because of the mountain range. Okay. That's just because that's the southern hemisphere. Okay. Prevailing wind direction goes east to west. What is that wind bringing with it? Humidity from the evaporation out of the ocean. It crosses South America. As it does, it starts to rain. And that's why we have a large rainforest here, right? It's getting a lot of rainfall. However, it hits the Andes. What happens when that warm, moist air reaches I'm sorry if anyone has a problem with that word, by the way. Okay? Moist. Yeah, I apologize if that bothers anyone. I've met many people that bothers. But humid air, let's say that, runs into this mountain range, and what can it do? What does it do? Can it go through the mountain range? No. Air can't go through rock. So where does it go?
Goes back.
Yes. Cross right there.
It stays right there. Goes up.
It goes up. What happens to its temperature?
It decreases.
It cools off. It decreases. And as it does so, what happens to the water content?
It goes lower.
Condenses, falls as rain. And so we get a lot of rainfall on this side of the mountain range. Ergo, rainforest. And all the cool, dry air makes it over the mountain range. It's rained out pretty much all its moisture. And you get this desert down here, even though there's an ocean right there, because the wind direction's going that way, not that way. So none of this evaporation goes that way. Only the cool, dry air that makes it over the mountain range gets to that side of this continent.
And it just takes up more.
Yeah, Chile is in places pretty chilly. Okay.
Who would have thunk it?
Who would have thought it? Now, all of these reasons for a mountain range. By the way, this is a cross-section example of that, okay? Makes it over, you get your rain shadow desert here. All of these reasons for deserts are because of what? There's one thing that controls a lot of the processes that we are talking about. No. The wind will be there regardless of this. The sun will be there regardless of this.
The tectonics that would make it so damp.
The tectonics. Tectonic activity. Without tectonics moving the plates around on the surface of our Earth, there would not be continents large enough for mid-latitude deserts. There would not be mountain ranges that block the rainfall, that block the warm air to make rain shadow deserts. There would not be land mass at the tropics of Cancer and Capricorn. Because of tectonic activity, these places are where they need to be in the arrangement they need to be to have these deserts form. It is completely possible that you could have an arrangement of tectonics where you have a very minimal amount of deserts. And as a matter of fact, there have been at various points on our planet when there is less ice, sea levels are higher, and therefore there's less continents exposed, not enough to really form a desert. There are points in our world's history, okay, in our planet's history, where there have been little to no deserts whatsoever. And there have been places where most of the landmass was desert. It just depends on whatever tectonic activity has occurred, okay, to put our landmass into the arrangement it needs to be, okay? It all comes down to tectonics at some point. Any questions about that? Okay. Let's talk about some processes that happen in deserts. Even though there is very little rainfall, there is still weathering. Would you say that in a desert that gets 1 day of rainfall per year, would you say that most of the weathering and erosion happens from that 1 day of rain or from 364 days of wind?
I have to assume.
The wind, okay. Wind. We all on board with the wind?
Yes.
All right, good. Y'all are wrong.
Oh.
Oh, no. Even if that desert only gets 1 day of rain a year, that 1 day of rain causes more weathering and erosion in that environment than the rest of the year of wind alone.
What? The area isn't used to water.
It's not used to water. Sediment gets washed away, just totally torrentially carried away. I was on a dig in Utah back in 2015. And super fun. But we took we arrived in this area. It was kind of rolling hills with some sort of steps. Do you know what a step is? A step is kind of a structure like that, and there's a valley, usually a streamlet down there. An ephemeral water body or an ephemeral stream, that's what we call it when it only has water part of the year. So like this right here, that's a stream bed, and here it is filled with water. It only happens a few times a year. That's called an ephemeral body of water. Okay, there are a couple of words for those: washes, arroyos, wadis, dangas, nolas, whatever. It just depends on the culture, the language. But regardless, so on this dig, we were in this place with all of these kind of steep-sided hills, because whenever this ephemeral stream filled with water, it would carry away a lot of material and make these hills. Okay. And so the one that we were on was kind of shaped like a ramp like that. We drove our trailer, we parked our trailer and set up our tents here on the top, okay, like that. And as we were finishing setting up, we saw some clouds rolling in. This thing's about 40 feet off the ground, okay? That night, rains. All night long, torrential, mind-numbingly loud, okay? This desert storm. And you just hear this rushing sound the entire night. And the next morning I wake up and I go and I look over the edge of our little step here, and the entire landscape had changed. The water had come about 30 feet up where we were. If we had parked ourselves down at the bottom of the hill, we'd be dead. I'd be dead right now. We would have been carried away in a moment. Luckily, we were anticipating something like this, so we parked on something that was tall enough to protect us. But all of the boulders and all the arrangements and even the shapes of all these hills were completely different than the day before. The incredible amount of weathering and erosion that had taken place, it was boggling. It was like we had to explore an entirely new place. Okay? So, even though it doesn't happen often, the intensity of these rainfalls in deserts and the fact that the ground is not well suited to absorbing that water, and so that water just kind of runs on top of it, accounts for the vast majority of the weathering and erosion that deserts do receive. Even though there is that small amount every day of wind doing its thing, it doesn't even come close to amounting or to accounting for the same amount that you get from water. Okay? So, let me erase this real quick before we move on to the next slide. Let's talk about that wind erosion. Y'all are pretty familiar with the fact that, yes, of course. Y'all are pretty familiar with the fact that air is a fluid, right? Not a liquid, a fluid. Both liquids and gases are fluids. Okay, they are substances that are bonded. They make some medium. Okay, so you and I are not swimming through the atmosphere right now because it is less dense than water. But air and water have a lot of things in common. They are a medium through which things can travel. Okay, that they can be compressed, they can be bottled up. Okay, they are both fluids. So water moves things using the energy that it contains, right? When my river is flowing downhill and it's carrying sediment with it, it's doing that because it has the energy to do it, right? It has the energy to pick that object up and carry it downhill with it. Air is the same way. But air does not travel in a river. Air does not collect in a lake or an ocean. Air, being a gas, just kind of floats in an envelope above our planet, kept here by a couple of things. Predominantly gravity and an electromagnetic envelope that keeps it from being stripped away by cosmic radiation. Okay? Rest in peace, Mars. Right? Now, even though air does not share that same cohesive property as water, and therefore is not as dense, it still contains energy. The more energy it has, we feel it, right? Just like that wave slapping your body, you can feel that energy. When the wind picks up outside, you can feel that as well. Now, at some point, you will even receive evidence that it has enough energy to carry particles with it. How many of you have ever been walking outside? Maybe you're at the Walmart parking lot. Maybe you're just out here. Maybe you're mowing your lawn, and the wind blows dust in your eyes. Like, oh, what the? Oh, come on, really? Right? Happens all the time. We have a lot of dust around here. We have a lot of wind. That wind contains energy. That energy picks up that dust, blows it in your eye. Just like water does. You have a suspended load, which is the particles that are carried in the wind, and a bed load, which are the things that are pushed along the ground. Okay? We call the process of moving sediment via wind saltation. This has nothing to do with salt. That's just the name for sediment that is being moved about by the wind. Saltation. That suspended load is normally the smaller particles, the silts and clays. In heavy winds, you can get a sandstorm. We get them here occasionally, right? Most of the time, though, your bed load is going to be the sand-sized particles, and your suspended load, the silt and clay-sized particles. And you can see in this picture, the sand blowing, or the wind blowing sediment, silt, clay, sand, whatever it is, right there across this hill. Okay?
Yeah, I've seen a bunch like when getting like a bunch like dirt or whatnot, just spiraling it.
Yeah. So occasionally you'll see what we call dust devils. Okay? Kind of almost look like mini tornadoes, right? Where a gust of wind has essentially turned itself vertical. Okay? This, for tornadoes, this happens because two different pressure fronts have collided together, and their rolling low and high pressure zones have turned vertical thanks to various physics. Okay? And that's what makes a tornado. In a dust devil, similar results, slightly different reasons. There's not like a high and a low pressure front colliding when it comes to a dust devil, but you still get the sort of swirling effect of dust and debris that you see, right? Now, when material is stripped away, removed from a location, we call that deflation. Like you're deflating a tire, except you're not deflating a tire. You are deflating the ground level. You are removing material, but it's getting stripped away by the wind, so your ground level is slowly decreasing. Okay? Normally, it takes away the smaller particles, those silts, clays, and sands. The wind generally doesn't have enough energy to carry away your larger particles, like your gravels and your cobbles and your boulders. And so those get left behind. And eventually what you end up with is what we call desert pavement. Desert pavement are all those larger particles. If you're ever walking out in the desert and just like you're trudging through the sand, all of a sudden crunch, 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 and you look, and all around you, whole bunch of larger rocks just kind of pile on top of each other, just this flat area of big rocks, like chunks of rock, hardly any sand, desert pavement. The smaller particles have been deflated away. Ventifacts and yardangs. Now, who invited Dr. Seuss to this party? I sure didn't. Ventifact. A ventifact is essentially what happens when a rock is exposed to the wind for a long period of time. It gets sand blasted. Y'all ever seen anything that's been sand blasted? Usually you sandblasting to remove paint or something else, some other, maybe a sealant from an object, usually only with metal or something that is just got the weirdest text.
Happens.
Yeah. Especially this time of year where it's all about, hey, please donate to my campaign. But it's from someone that I've never even heard of. I think this one is from some politician in Hawaii. I don't know. Yeah, it was weird. I'll look at it later. But you get this smooth, polished, glossy surface there because of the sand blasting effect. It's removed all of the little ridges and imperfections, and it's made this nice, smooth shape. And it will often actually also take on a sort of streamlined shape in the direction that the wind was coming from. So in this particular case, it's kind of got this three-pointed shape. This rock probably experienced this sandblasting effect from three different directions while it was there. Now, if I took this and I pulled it out, whatever was under the rock, whatever was under the rest of the sediment there would not be sandblasted. It would be that rough, whatever the shape of that rock was before, unweathered, untouched by that wind. Okay, only the top surface, whatever has been exposed, will have that look. That is a ventifact. Yardang, that's actually a Pakistani word. Okay, yeah, yardang. Yardangs look like this. We have these around here. Okay, you'll see these every now and then. A yardang is some rock formation that under high winds, yes, of course, under high winds is shaped, is weathered down into this sort of mushroom shape. Why would that happen? Why would it make this mushroom shape? Why would it not weather down uniformly across its entire surface? What is causing this?
The wind hitting it.
Huh?
Like the wind hitting it. Like,
The wind, sure, but what's the wind doing?
Hitting it from different angles.
Let's assume the wind is coming in one direction.
Okay. Does it have to do with like I guess clearly like imperfections in the actual rock itself?
Nope, doesn't have to do with imperfections in the rock. Has everything to do with the wind.
trying to disperse how like the wind like erodes it.
The wind is in fact weathering and eroding here with what? Is there anything inherent about wind that can cause weathering and erosion? No, it's air. What is it? What is causing the wind and the weathering and erosion? What the wind brings with it, which is sand.
Wow.
And where is the sand?
On the ground.
On the ground. It's the bed load. So we have wind blowing. Okay. Actually, it's probably blowing this way. Okay. So the wind is blowing. Okay. And as it's blowing, it's pushing sand along the bottom with it. There's probably some silts and clays, maybe a little bit of sand at some times carried in the suspended in the wind. But for the most part, where is that sand? On the ground. Therefore, as the wind is blowing that sand and that sand is blasting into this formation, where is the most weathering going to happen? At the bottom. And so you get this weathered sort of sand-blasted pillar, and then the formation sitting on top of it, making this mushroom shape. That is a yardang.
And that only happens when it's pushing one direction.
It can push multiple directions, but you can usually tell what the dominant direction is because your yardang will be shaped in the direction of that wind. See how this is kind of taken on the cross-section of an airplane wing? That tells you what the dominant wind direction of this was, because that is the natural shape that things will take on given enough time under the influence of that wind.
Is that why we have like wind turbines like that in a way?
That's why, yeah, well, that's why wind turbine blades, that's why airplane wings, that's why helicopter blades, that's why they're all shaped like that, because they are aerodynamic. Okay, they take on that cross-section intentionally. Okay. Now, what happens to that sand as it gets blown about? It eventually is going to get piled up. Ah, yes. What do we call it when it gets piled up? It is a dune, sand dune. Okay. So as these piles of sand get higher and higher eventually, what's going to happen is it's going to take on a very distinctive shape. Okay. Our distinctive dune shape looks something like that. Okay. As the wind is blowing in a certain direction, grains of sand are going to get shoved up and around this shape. The wind's going to gradually carry it there. And then eventually the wind isn't going to be able to carry it anymore. What's going to be driving it? On this downhill, what's going to be driving it?
Gravity?
Gravity. Gravity takes over, which is why you have a steep side here and a gentle slope here where the wind is pushing it up, fighting gravity. And then once you pass this point of no return, so to speak, gravity takes over and you get that steep side as the sand slips down there. As a matter of fact, that's what we call this. This is the slip face of your dune. Okay? This is the slope. That is the slip face. And these dunes do, in fact, move. They move in the direction that the wind is pushing the sand. Whatever that dominant wind direction is, it'll go there. So there are several different types of dunes. There are actually many. We'll only go over 6 today. Okay. The first one that you're probably most familiar with, this characteristic shape of a dune, this is called a Barken dune. Kind of has this crescent shape like that. Okay? Where this is your slope and that's your slip face right there. It is crescent shaped with the crescent pointing in on the slip face. Why do you suppose this pile of sand would take on this crescent shape? Are they dead over there? No? Doing okay? Sorry if today's lecture is a little dry. Okay. Thank you. Okay. Why do you suppose it's taking on this crescent shape?
This also feels like that water thing where like most of it's in the center, and it just like has less going out.
Okay. More words. Let's think about the energy happening here.
More energy is like within like the center of the one, I guess.
To push sand up the middle, up the slope, does that take more or less energy than to push it along the sides? It takes more to fight gravity and push up there. And so yes, the sides of my pile of sand are going to extend out in front of the main body, making that crescent shape because it takes less energy to push sand out that way. So even though my entire dune is moving, the sides are moving a little faster than the middle. Okay, so that's what makes that crescent shape. Okay, you tend to get these where you have you've got limited sand. Okay, so you have individual piles. On the other side of the spectrum, where you have lots of sand, you get what we call transverse dunes. Now, someone tell me what this reminds you of. Waves. Does this look like waves to y'all?
Yes.
Okay. Explain why that might look like waves. Okay, yes, it's wavy, but I mean, that's not helpful. Whew. Rough start to the week for everyone.
I'm just trying to process.
Yeah, I know.
Why it may look like waves?
Yeah.
Is it like you said, like
Because it's really windy.
the wind is flowing up, but it's like the gravity is pulling it down, and it's just doing that over and over again?
Less to do with gravity, more to do with the physics that are going on here. Why do waves in the ocean look like waves? We haven't quite talked about this yet. But what is water? It's a whole bunch of individual water molecules that are cohesively joined together. What is the ocean? But a whole bunch of those molecules that are under the influence of wind, making those wave patterns, right? What is a desert with lots of sand, except the same thing, but with larger, denser particles? The same physics are going on here, the same energy from the wind. It's just going a lot slower. So yes, those do look like waves because they are under the same physics as the waves in the ocean are, just moving a heck of a lot slower.
And is the other one just moving faster than that one?
This one has less sand. And
The one below.
this one,
Yeah.
this is a barkenoid. This is like between those two. If you have a moderate amount of sand, you're basically going to get a bunch of barkens that are joined into those waves. And so your waves don't look nice and neat like they do in the ocean now. They look like crescents that have been joined like that. Okay? It's between those former two. Okay? Like barkens that have been squished together. Then we have longitudinal dunes. In high winds, your Barken dune is going to have the sides stretch out way further than your middle, right? And so you're going to end up with an elongated crescent like that. really strong winds have stretched your Barking dune way far out. That's a longitudinal dune.
You're missing the palm on Viva Trades.
What?
The Apollo Trades.
Polytrades, Lisan al Gaib. Different dune, but yes, no sandworms here. All right. Then we have parabolic dunes. This one's fun. I wanna ask this table over here about parabolic dunes. Okay, I'm gonna ask you. You ready for this? We have learned that your typical dune is crescent shaped like this, pointing in the direction that the wind is coming from. In a parabolic dune, it's still crescent shaped, but in the opposite direction. Can you think of any reason why the crescent shape would switch like that? We learned that it takes on this crescent shape over here because the sides move out faster than the middle does. So what must that mean about our parabolic dune? If the sides move faster than the middle over here, then over here, what?
Wait, say it again, please.
The sides move faster than the middle over here, which means that over here, which is moving faster? The middle. Now, in what situation would the middle of my dune be moving faster than the sides? What could cause that?
Something that is holding the side.
What's holding the sides together? Plants, vegetation, bingo. Okay, so we have shallower sand on the sides of our dune. Deeper sand in the middle. Shallower sand, easier for plants to hold together. Deeper sand, not as much of it is held together. Therefore, whenever there is vegetation on our dune, the sand tends to move faster in the middle than it does on the sides because the plants are holding it together on the sides. Parabolic dune. Boom. Okay? Well done. Good job. Now, the last type is a star dune. With a star dune, you get these crescent shapes, but there's a bunch of them for each formation of sand. Why would that happen? Wind direction changes fairly often, right? And so you get these crescent dunes that kind of intersect each other. Every time the wind changes direction, a new dune is formed pointing from that direction. So if you, how many of you have ever been out to the Monaghan sand dunes? It's a combination of Barking dunes and star dunes mostly. Okay, a few parabolic in there where there's more vegetation on them than others, but for the most part, you see a lot of star dunes over there because the wind direction around here is pretty fickle. It changes seasonally, by day. It'll go one direction in the evening, the other direction in the morning. Okay. Any questions about dunes?
Are they hard rocks of sandstone?
No, the dunes are loose sand. They are not rock. Not yet. As a matter of fact, any of you that walk out on the third floor and you go to the, you know, the study area, the lobby up there, there is a picture of some red and orange rock up there. And you can see cross bedding in that picture. That is a dune. That's a bunch of dunes that have been preserved as rock. That's what the cross bedding is. Dune piled on top of dune, piled on top of dune, piled on top of dune. And then it got turned into a rock. That's what that picture is up there. I've often wondered why they have that picture up there and not down here with me. But maybe I'll just steal it one day. Shh.
They won't know.
Now, that's what the sand does. But remember, that's the bed load. What does the silt and clay? Often the suspended load, right? What does that do? Well, it's in the wind. It gets carried away. And sometimes it gets carried really far. This is the western edge of Africa. That is the Sahara Desert right there. Look at all this dust being blown off of the Sahara Desert across the Atlantic Ocean and ending up where? Where is this? Where do y'all think this is?
That's the Caribbean.
Yeah. Where's this?
Cuba.
That's Cuba, right? Here's Central America. There's the Yucatan Peninsula, right? Here's the north coast of South America. All this dust being blown off of the Sahara Desert, across the Atlantic Ocean, ending up over here. People in Central and North-South America are farming using Saharan soil. They probably don't even know it. That's a very strong wind, right? It's not always like this, but you can actually drill down into the rock at the bottom of the Atlantic Ocean and see layer after layer after layer of Saharan dust in the layers at the bottom of the ocean. Okay? Now, that dust, we call it loess. L-O-E-S-S, loess. Wind-blown desert dust. And thick layers of loess make a very hard brick-like rock, which is difficult to dig into, but once you have dug into it, it's very sturdy, okay? People for many, 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 many years have found layers of loess like this and dug into it to make their communities or their houses, okay? Difficult to get into, but once you do, it's solid, okay? Now, there's something pretty cool about desert soil I want to point out real quick as far as it intersects with human civilization. I'm going to tell you a story, okay? Thousands of years ago, a migrant group of people ended up in East Africa, northeastern Africa. These are people who just kind of wandered place to place, like most humans did at that point in time, going from one location to another, hunting food, foraging where they could. But they ended up in northeastern Africa. There they found a river, beautiful river, large, plenty of fish. And they found that along the banks of this river, they could grow things really well, constantly. So they decided that they wanted to stay there. They pitched their tents, they built a community, they started building buildings, they started building cities. Their agriculture grew and grew and grew. Okay? Pardon the pun, I guess. And they started to gain a reputation. This farming community in Northeast Africa started providing food to other neighboring civilizations and communities. More and more people started to join them because of the richness of the land that they had settled in. And so finally, they went from a group of farming communities to an actual civilization, one that we all know the name of. They made the Egyptian Empire. Now, what happened here? The soil on the side of the Nile River is the richest soil in the world for growing. For a couple of reasons. It has the constant source of water from the Nile, but also wind-blown loess from Africa or from the Sahara Desert. That loess blows into the river, gets incorporated into the soil on the sides of the river. Why is this loess so special? How many plants are there in the Sahara Desert? Hardly any. So how used is that mineral content before it makes it into the Nile? It doesn't get used at all. And so you just have this mineral content that has been broken down over and over and over, never used. It's, I guess you could say, it's nutritional content for plants, top tier. and it gets put in that water and incorporated in the soil on the side, anything will grow in that. It's amazing soil. They literally ship that soil all around the world. If you want the best growing soil, you get it from the side of the Nile, right? Because of the location, the proximity to that desert. And so, yes, the Egyptian Empire, which lasted 5,000 years, owes its entire existence to the simple fact that that wind-borne lust, that dust, was perfect for growing plants. How about that? Shaped human civilization, right? All right. A couple more things. You're familiar with our alluvial fans that we get that form at the base of mountains or other high elevation areas as water carries sediment downhill and deposits it when it loses energy. Well, the same thing happens in a desert. Even though you may only get that one day of rain a year, it carries a lot of material downhill when it does. And so you get these aprons of sediment, which are, yes, alluvial fans, okay? Here at the base of your desert mountain ranges. These are all ephemeral bodies of water. There's no water in them right now, but you can clearly see there's a fan, 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 right? Still happens out there. A playa is what we call a wide, flat area where once water was, but has evaporated away. These are usually covered in salt or gypsum deposits. Okay? Tons of these out in Utah. If you ever fly out there, take your sunglasses. Or if you ever drive out there, take your sunglasses. You don't want to get blinded. It is extremely bright on the playas out there. And just because I know you all have been wondering this entire time, well, what happens to a volcano that gets incorporated into a desert, right? Y'all were thinking that, weren't you? Well, rightfully so. We call that an Inselberg, okay? A volcano around which a desert forms gradually gets kind of weathered and broken down until it makes this, I can't think of any other way to say this, but sad shape. Like, okay, you know what this looks like to me more than anything? It looks like a half-melted Hershey's Kiss. Yeah, it's just this poor volcano, right? But you can see all the dunes that have built up on this side of the volcano, and then over here, no dunes at all. Why? Because the wind is coming from that direction. And so there's more weathering and erosion happening on that side of our volcano, and the sand is encroaching from that side, and it's kind of making this shadow effect over here. We call this an Inselberg. And that's our lecture, folks. Any questions?
I think if you look at glass formations under those, like, how would that be?
How would what be? I'm sorry.
Like, you know how when you picture desert, you think like sand, glass. Like how would that,
Glass?
I think it was sand, like glass in that volcano.
Glass in the volcano.
Or
You
Not
cover
like
the
that.
sand? Is that what you're trying?
yeah.
This is not an active volcano.
I know it's not, but like we just. I think there would be like unique glass formations under there, something like that.
Not particularly. No. This is an extinct volcano. Its heat source is long gone.
Like in an active volcano, what are the minerals that get formed? Are the same minerals in a normal volcano?
Yes, whatever the environment is outside of this volcano has nothing to do with the processes that go on in its magma chamber or with whatever the composition of lava it expels. Okay? If this volcano was in the Amazon rainforest, it wouldn't make a difference. If it was in the Sahara Desert, if it was in Antarctica, wouldn't make a difference. The chemistry of the magma would not be affected by the exterior environment.
I don't know how long that volcano lasted. So it was just in a bunch of
Don't know.
sand.
Don't know.
Like it'd just be constantly pelted by a bunch of sand. Still out.
I mean, eventually it will break down. Right? All right, any other questions?
I didn't really think about it, but I guess it kind of does make sense that there could be polar deserts as well.
Yep, polar deserts. Yep.
What about polar volcanoes?
Yes, there are volcanoes at the poles. Not very many, but there are some. I can't think of any that come to mind that are currently active on Antarctica. Antarctica is a weird place tectonically because
There's no one plate that it sits on.
no, it does sit on a plate. It's got its own plate. But that plate has been sitting at the bottom of our planet at the southern hemisphere for tens of millions of years and has not moved. We can't even predict if it ever will move because it is not currently moving. So we can't say where it's going to be. It's very interesting, and you'll see this more in 1404. But when you look, huh?
It keeps moving. How is that one not?
Because it's not. I mean, there's probably no convection underneath of it at the moment. But as far as we can tell, it has been sitting there for, I think, 70 million years almost without hardly moving. Yeah, without hardly moving at all. And so when you look at the models that people generate of this is where our plate tectonics will be in 100 million years based upon their current trajectories of motion, Antarctica is still sitting down there at the bottom for all of these models because it is not moving and therefore we can't predict where it could go. Yes, of course. We'll talk more about that in 1404. I love that you all ask questions that are in depth enough that I have to say we will discuss it in the next level of the class. That speaks great things for the way y'all are thinking.
Do the projections like vary wildly, or is it like
There are some wild differences, but no, most things they tend to agree on. Okay, I'm going to end the recording here.